On June 4, 1937, in Racine, Wisconsin, several skeptical engineers met to spectate a full-scale test for a unique column designed by Frank Lloyd Wright for the Johnson Wax headquarters. The column was said to be too slender at its base to support the load of 6 tons that it was required to hold. The column surpassed the required weight and was able to hold 60 tons before failure, 10 times as much as was required. So, how exactly could a column, whose base tapers to an astonishing 9 inches in diameter, hold so much weight? The architect's faith in the column was due to his knowledge of the stress and strain properties of the materials used. Stress is defined as the average force per unit area, or F equals P over A. The P is the force acting upon the object, and A is the area that is resisting against the force. There are 2 kinds of stresses: normal stresses, tensile and compressive, and shearing stress. Tensile stresses elongate a member, while compressive stresses shorten a member. In both instances, the resisting area is perpendicular to the force being applied, while shearing stresses describe forces that are parallel to the area they are applied. Strain is the resultant of stresses placed on the column. It is the measure of deformation along the length of a member. Axial strain can be traced by the equation sum of forces equals deformation over member length. In this case, the column was resisting compressive forces and thus was experiencing compressive stress. The engineers assumed the column would fail because they believed the column didn't have enough area at the base to resist a 6-ton axial load being placed on it. The column's geometry was also irregular, so stress could no longer be assumed to be uniform across the surface. Because of these reasons, the engineers assumed the column would experience too much strain and collapse under the required weight. The engineers believed that the narrowness of the base of the column would cause a stress concentration that was too great and would result in failure. They failed to account for the fact that the base was made of steel, a ductile material that has the tendency to yield, causing a redistribution of stress across more of the cross-section. It was this redistribution of stress that allowed for the base to fall in the permissible stress range. This phenomena can be easier explained by looking at a stress-strain chart, where the various points of failure can be traced. Deformation due to strain occurs at the yield point. However, this point varies for different materials. Once a material passes its yield point, it stops deforming elastically and begins to deform plastically, meaning that the object will no longer turn to its same shape after the applied stress is removed. Ductile materials, such as steel, have a large modulus of elasticity and therefore are able to resist concentrated loads better than brittle materials, such as concrete. Although brittle materials are still mildly elastic, they reach their yield point much earlier and usually will remain in an altered state after an excessive load is placed on them. This material concept can be better explained by elaborating on elasticity. Elasticity is a property of materials where when a load is removed, the object returns to its original state. Almost all structural materials are elastic to some extent, but as stated before, ductile materials have a tendency to resist deformation more than brittle materials. If a load remains below the yield point, or elastic limit, the object will return to its original state. Anything beyond that and it will remain permanently deformed. This state is often called inelastic. An object that has passed its yield point is considered in failure, but this does not mean it has ruptured yet. Rupture doesn't happen until after an object reaches its ultimate stress, the point at which a material fails completely because the load placed on it is too excessive. Unlike ductile materials, which fail gradually, brittle materials will show few signs of failure until their point of rupture. This is called catastrophic failure. In the case of the column in the Johnson Wax building, the failure happened to be catastrophic because although it was composed of both concrete and steel, the majority of the exposed member was concrete. Frank Lloyd Wright was able to achieve his vision of these tree-like columns because of his comprehensive understanding of these material properties and structural limits. The hollow steel tubing and footings used inside the column were able to exponentially increase the capabilities of the non-uniform columns. This understanding helped him realize one of the most unique visions in architectural history, and was to become one of the greatest defining moments of his career.